Okay, so here we're looking at metallic bonding. Here we have a diagram of metallic bonding, and quite often it's described as a lattice of ions in a sea of electrons. So right here we have a metal ion. Okay, it's a metal ion because it's lost an electron. The electrons have become delocalized. So these little purple dots represent the delocalized electrons. And they can move throughout the structure. They're not tied to just one atom. They've left their atom and they can move throughout the structure. And the actual metallic bond is the electrostatic attraction between the metal ions and the delocalized electrons. So these metal ions are attracted to these delocalized electrons. The positive, the negative, is a very strong attraction, and that is what makes the bond between the metal particles, the metal atoms becoming metal ions, being attracted to the delocalized electrons. Very strong metal bond is formed. So why do metals form this type of bonding? Why can they have delocalized electrons? Why can their outer electrons and their outer shell electrons move away from the atom? Well, metals have lower ionization energies than non-metals, going along the same of the same period. Okay, if you think about it, the metals are here, are all on the left-hand side of the periodic table. So as we go across a period, the ionization energy increases because we get more protons in the nucleus for the same amount of shielding. And all the metals lay on the left-hand side of that period, so they have lower ionization energies. So the reason that they have that is because they've got less protons compared to non-metals of the same period. And they're also bigger. Okay, remember that the atomic radius decreases as you go across a period. So compared to other things in their period, compared to the non-metals within the period, they have a larger atomic radius, they have less protons, and so it's easier to lose their outer shell electrons. And those outer shell electrons become delocalized throughout their structure. So what properties does this lead to then? Well, metals have high melting points. Because of the strong attraction between the ions and the delocalized electrons, it takes a lot of energy to break that strong attraction, break that metallic bond, and so they have high melting points. They're ductile and malleable. So ductile means they can be stretched out into wires. Malleable means they can be bent and hammered into shapes. And that's because the layers of ions can slide over each other. So if we just go back a bit to here, these layers can slide over the top of each other because the delocalized electrons will always be buffering in between. So these ions will never repel from each other because they will always have some delocalized electrons in between. So it doesn't matter how precisely they line up. Not in the same way as an ionic solid does, which is very brittle, because if in an ionic solid, if the plus was in line with a negative ion, it would repel. If a plus became in line with a positive ion, it would repel. In this case, there's always delocalized electrons in between, so the layers can slide over each other. And they can conduct electricity, and that's because they've got the delocalized electrons, which are free to move. So when a potential difference is applied across a metal, so when a voltage is put across, it's attached to a battery or something like that, the electrons will move through the wire, through the metal. And they can do that because they're delocalized. They're not attached to just one atom. So are all metallic bonds the same strength, or are they different in different metals? So if we can compare sodium, magnesium and aluminium. Sodium's in group 1, magnesium's in group 2, aluminium's in group 3. When they form ions, they form with these charges. So the sodium ions 1+, magnesium 2+, aluminium 3+. And that means that the aluminium has a stronger charge on its ions compared to the magnesium and then compared to the sodium. If we think about the size of the ions, these all have, once they form ions, they all have the same electronic configuration, but this one has more protons, and so it's a smaller ion. It also has more electrons, more delocalized electrons, because it's got 3 in its outer shell that have become delocalized, while sodium, for example, has only got 1. So aluminium then has the strongest metallic bond. That's because it's got the strongest charge, the most delocalized electrons, and the ions are smaller, so that means they can pack tighter together. And overall, that means there's a greater attraction. That gives it a stronger metallic bond.